Talking about the diffusion, right? Diffusion. Why do you have to talk about the diffusion? In the integration, the most basic principle to level up the integration is to make the transistors small, miniaturization. That is the important thing, right? And for the MOS, it is going to look like this. And this is the junction depth. And the junction are to be made by the diffusion of the doping species in the silicon. And this junction depth it should be less than 1,000 angstrom. So the diffusion of dopant in the silicon has to be precisely predicted and controlled to make the transistors sub-micron transistors for the ULSI, right? So we have to talk about the diffusion. In the diffusion, in the discussion of diffusion, we mainly have to talk about the fixed second law. And fixed second law says the diffusion profile. This is actually diffusion profile. And that is round X right? This is the general formula for the fixed second law. And when D is not a function of X or a concentration, it's the same token, and it's not a function of time, then we can simplify this equation to D round X round this partial differential equations. But if you want to control the junction depths this precisely, then first you have to check whether that diffusion coefficient is not a function of X or the dopant concentration, etc., okay? If not, then you cannot use this simplified diffusion equation, fixed second law, for controlling the junction depth. So that is the point, okay? For the bipolars, we are having situation like a buried layer, and then junction separation with the next one, and then if it is a let's say this is going to be collector, and that is the M minus where's my pen? And this is the base a P minus, and we should make a diffusion of N plus here, and that is emitter. Okay. Emitter. Okay. And the important size here is this base width. Okay, the base width has to be controlled less than 1,000 angstrom as well. And this base width is totally dependent on the diffusion process. All right? So we have to understand the diffusion coefficient, diffusion behavior of the dopant in the silicon more precisely. And that's why we have to talk about the diffusion first in this class. All right? Well, the one thing I have to mention is that when we have this kind of structure, it turned out that we are having some kind of extra depth, delta, and delta is called emitter push. Emitter push. That is pretty bad for the bipolar transistors. And that thing happens because of this environment. If you have a boron and then on top you diffuse your phosphorus, for example, for the emitter, then this phosphorus creates a lot of vacancies inside the boron doped region, so that the area, the region which is just beneath the N plus is going to have an extra diffusion of the boron. And that can be explained, okay, in this class. So this kind of feature is very important for the ULSI. So that's why we have to talk about the diffusion, and then we start out with a point defect, because this point defect is a critical parameter. The concentration of a point defect is a critical parameter for the diffusion process. And this is the thermal equilibrium properties. Thermally equilibrium properties, so that we can make a prediction of this. And then vacancies, the typical point defect in the silicon is the vacancies, and this vacancies has the charges, and that is a very important feature, right? And these main dopants in the silicon diffuse with substitutionally, which means it has to be coupled with vacancies. And this is a semiconductor. I think you have to go to the Mr. Love here to get a new pen, okay? So that the dopant has charges like, for example, the acceptor it has to be charged with a minus, and the donors like phosphorus, arsenic, and antimony, typical donors, themselves has to be charged positively. So for the diffusion, this dopant atom has to be coupled, and if the vacancies has charges like neutral and negatively, doubly negatively, positively, doubly positively charges, something like this, and then we can locate the energy levels from the conduction band and the valence band, such and such. This not observed experimentally, so we just neglect this. And then mainly we have these 4 charges. This neutral, it can be coupled with any dopant materials, but once it has a charges like this, then it should couple with the opposite polarities. So first we have to know what is the concentration of each charges, and the total diffusion coefficient is going to be related with the each coupling, like diffusion coefficient is neutral plus negatively charged, doubly negatively charged, and positively charged, and doubly positively charges, and we just neglect this. So basically we have these 4 terms to make a total diffusion coefficient of any species. Now if you want to talk about the boron, then we don't have to worry about these 2 diffusion coefficients, because it cannot be coupled with the same signs, right? If you want to talk about the phosphorus and arsenic and antimony, then we don't have to talk about this one. And we have 3 terms, a little bit more complicated than the case for borons. But even if we have these 3 terms for the anti-dopants, depending on the temperature and the doping concentration, among these we have a dominant species, and we don't have to worry about the other terms except the dominant terms to get the diffusion coefficient, right? And here we have n square term in front of the double minus, so that the concentration of the dopant has to play an important role, even though this value is small because of the concentration of doubly negatively charged vacancies is small at a certain temperature and doping level. We have n squared should be multiplied to this to get this term, so that sometimes, even though this vacancy concentration is not important, the doping concentration is high, then this term cannot be neglected anymore. Okay, that happens, and especially in the phosphorus case. What we are going to see. So right after we determine the diffusion coefficient at a certain specific conditions, the next thing that we have to do is we have to really solve the fixed second law. Okay? So far we have determined this diffusion coefficient. So once we have a diffusion coefficient, from now what we are trying to do is we are going to solve the diffusion coefficients accordingly. So today we are going to talk about the arsenic, and the next Monday we're going to talk about the phosphorus. It's a little bit complicated. And then finally we are going to talk about the boron diffusion profile. This thing is related to the diffusion profile. Diffusion profile. Okay, let me see. Once you have a diffusion coefficients, okay, then you just set up the equation, and then you can use the computer for the numerical solutions. But what we try to do is here in this class is that analytically you want to solve this to find the physics inside, what's happening inside the diffusion process. Okay, so we are not going to just use the computer to get the numerical solutions of this equation. Even after we find the value for D, we try to solve this analytically to find the physics inside the diffusion process. And we're going to do the arsenic first. Okay, turn. I think at page 24. Okay. Impurity diffusion profiles, 4.4. The material in the last set of note, we just calculate the diffusion coefficient. Okay. Now, diffusion fixed first law and fixed second law. This is the fixed second law, and if diffusion coefficient is constant, then we can set the equation 3 here. Now, in most of the cases, when the concentration of the dopant is not that heavy, it's lightly doped case, we normally we can use these approximations. We can assume the diffusion coefficient is a constant. In metallic systems, not this semiconductor, in a metallic system, we almost all of the cases we can set the diffusion coefficient is constant, no matter what. Heavily doped or lightly doped, it doesn't matter in a metallic system. But in an insulator and semiconductors, the vacancies has to be charged so that we cannot set the diffusion coefficient as a constant most of the times. But exceptionally lightly doped, we may use the diffusion coefficient as constant even in the semiconductors and insulators. Now, here I showed some of the examples when we can use this fixed second law, approximate the second law. The pre-deposition and drive-in for the doping, when we know the boundary conditions, and when we can solve the fixed second law, assuming the diffusion coefficient is constant, and we have a complementary error functions as a solution for the pre-deposition process, and we have a Gaussian profile for the drive-in. And when you draw that, we see in the pre-depositions the surface concentration is fixed to the solubility limit, while in the drive-in case, the surface concentration is continuously decreased to flatten out the doping concentration. So we have two different situations like this. And the profile here is a complementary error function for the case for pre-deposition, and this is the Gaussian profile. Now, diffusion under extrinsic doping conditions. In the general case, we have to set this, and in general, we have seen this. The diffusion coefficient is going to be consist with this 4 terms. We neglected the double plus vacancy, doubly positively charged case, because we cannot observe them in the experiments. And here you can notice that we have electric field term, electric field correction term. We're going to talk about this in a minute, okay? In semiconductors, it does create the electric field if you have a concentration gradient. Here, let's suppose you have a concentration gradient along the depth, along the distance, then this dopant concentration will create the potential difference, of which slope is representing the electric field inside the semiconductors, built-in electric field. Okay, so we have to take into account of this electric field in the total diffusion thing, especially for the neutral ones. We have to put this electric field term here, and then in this electric field sections, we can calculate what that could be. And in this electric field effects, we don't have to think about the neutral terms like B minus and V plus coupling as a total is a neutral. So we don't have to take into account of the electric field term for that species. Okay? And electric field effects only apply for the negatively charged one, B minus and V neutral, or here was some of the missing here. B only, okay, this is not a coupled boron, which we don't have to really worry about in this diffusion process. So this is the negatively charged one, and for the case of N-type dopants, we have to worry about P plus and the neutral, things like that, okay? Let me just, net charges. The case where we have net charges, like, when do we don't have to turn on the light. I think we use that. Net charges, when the B minus is coupled with the positively charged neutral vacancies, it has negatively charged. And then if B minus and free double plus, it should have charges. But see, this is not really important in the real practice. Okay? So for the P-type, for the boron, this may be the important thing that we have to take into account in electric field term, the H values. How about the phosphorus and arsenic and an antimony case? Maybe this coupling also positively charges, net positive charges, and we have doubly negatively charged one. We have net charges here, and this is important in case of phosphorus. The other terms we can talk about the same thing. The neutral, the electric field is not important in the neutral case. neutral. And then the neutral thing, of course, the vacuum neutral vacancies and B minus and B plus is the net neutral, okay? And then phosphorus, V minus, it is neutral. So we don't have to consider the electric field effect on those terms. Okay? And the impurity itself, impurity gradient will set up electric field inside the semiconductors, and that can be seen in this equation. Okay, and total impurity flux, atomic flux in the presence of a chemical and electrical potential, that is going to be called electrochemical potential, right? Electrochemical potential. Electrochemical potential. We usually use this term, and it consists of electrical field term and the chemical terms. Okay, and this is a drift flux, and this is a fixed second law. All right. So here we had that equation here, the flux, total flux in the presence of electrical and chemical potentials. We have to use this equation in the metallic systems. We don't have to worry about this electric field term, because in the metals there are so many free electrons. We cannot have electric field inside. So in the metallic systems, we don't call electrochemical potential. We just say chemical potentials. Okay, gives free energy and all those things. But in the semiconductors and insulators, we do have to think both terms, so that we usually call the electrochemical potential, and the total flux consists of diffusion and the drift flux. Okay. And using Einstein relations, we can use diffusion coefficient for the electric for the drift, and then we know the concentration of dopant is related to this in this fashion, and then this electric field can be represented on this, so that this is the equation corresponding to the electric field, which is going to be set up inside the semiconductors due to the concentration gradient of the dopant, right? And we can see the electric field enhancement factor, H, is going to be represented in this equation. And one thing you should notice is that the value of H cannot be more than 2. All right? The enhancement of a diffusion coefficient due to the electric field effect is at most the 2. It can be doubled and nothing more than that. And if you have this kind of situation, once you have a base diffusion, and then on top of it, if you want to make an emitter so that you want to diffuse the M plus, we can set up the electric field plus minus, and here minus plus, because of this concentration gradient. And then your diffusion species is, in this case, the positively charged one, and here is the negatively charged one for phosphorus and boron. and so that the electric field effect enhancement due to the electric field may work differently. Now let's just read a little bit on this here. Impurity diffusion will be aided with the electric field, of course. This is the neutral, so that that should not be affected by the electric field. And the M plus region direction of electric field is set by dopant concentration gradient, and this is going to be retarded, and that is going to be enhanced because of the electric field works differently. Okay. Now let's talk about the arsenic diffusion profiles. And firstly, I just listed the references. So if you want to, if you're really interested in some part of this discussions, you may go for the references here. And for the arsenic, we have applications like in a CMOS, MOS devices. The junctions are made with the arsenic because the diffusion coefficient of arsenic is very much low than the diffusion coefficient of phosphorus thing. Okay, so it is very beneficial in making shallow junctions of the arsenic. So most of the source and drains in the MOS devices, we use the arsenic in this case. Here, the emitter, we want to have a very shallow emitter, so that we have to use a arsenic for the emitters in the bipolar transistors. Okay. And we have seen that diffusion coefficient of arsenic is going to be represented by this equation. Okay, here the first term is the coupling of arsenic with the neutral vacancies, and the second term is the arsenic coupled with the negatively charged vacancies. And the other terms are not important for the N-type materials, right? And in actual fact, we should expect this term, diffusion, be affected by the electric fields. And it says the pseudo-electric field effect, which says we have to use this equation experimentally. Okay? We don't know the reason. Here it says a good explanation is lacking at present, but empirically we have to use this equation so that from the experiment we can use the constant values to finalize the diffusion coefficient of the arsenic. And this is the experimental plot. Says calculated values of diffusion coefficient of arsenic. And these values have to be used. These values should be used for the actual arsenic diffusion calculation, using the above form diffusion coefficient, assuming that the negatively charged vacancies are dominant. We can set the profile, the equations that we have to solve. This is the fixed second law actually, and this diffusion profile is going to be represented up to these equations here. Okay, and this equation actually can be solved numerically by the computer, but we can solve this equation, approximate the solutions analytically, and then the result is given here. This is the surface concentration, in other words, the solubility limit of the arsenic, and the concentration profile is going to be represented with this equation where the y is going to be this, okay? And then here the lines are corresponding to the theories, calculations, and the points here is the experimental results. And you can see it's pretty much matching, right? So the equation is not that bad. And this is the actual profile, the concentration and the surface distance in the microns. And you can see it's almost a box in case of arsenic. Only when it is heavily doped, okay? When you have a heavily doped situation, the arsenic shows this box. So the next of this note says about the approximations. We can have approximations regarding this as a box, okay? And then, the area here is the concentration of the arsenic. And then the distance from the x and y, you just multiply x and y to get the concentration. Okay, this is a solution. This is the solution that we use the analytical method. And then we just approximate this, assuming it's a box, 0.053. Okay? And then we can have this simplified equations to have this is the experimental results and this assumptions, box assumptions. And then you have a pretty much on the line. Every experimental results are sitting on the lines, as you can see here. And then we convert that concentration of arsenic to the sheet resistance, because that's just a one-to-one match, okay? The dopant concentration can be matched to the resistance in a semiconductor. So we just use this equation to get this y-axis as the sheet resistance, and this is actually the distance. And you can see the pretty much close matching between the calculation and the experimental results. Okay, so in an arsenic case, since it shows this box type and this theoretical profile actually is going to be applied for the heavily doped arsenic case. Because only heavily doped arsenic case, the diffusion coefficient can be defined with there's two terms. Okay, in the lightly doped, then V double minus is going to be dominant. Because the charged states of the vacancies is dependent on the ferromagnetic level, location of the ferromagnetic level, and then the ferromagnetic level location is dependent on the doping concentration. Okay, if you have a heavily doped semiconductors, ferromagnetic level is going to be located close to the conduction band, and in that case, V double minus vacancy is going to be the dominant species. And then we have another term here, the third term. But in a heavily doped case, okay, this V minus will be dominant, so that the diffusion coefficient can be simplified with these two terms. And in the two terms, then the solution, we can have analytical solutions for the diffusion profile. And then this is the actual case, and that the theoretical values you can see in a heavily doped region, highly doped regions is pretty much matching, right? We don't know about this lightly doped arsenic case. All right? So that's a box type, and then with a box you can make very simplified equations representing to the diffusion profile, all right? So that we can have a pretty much predictions. We can make pretty much predictions about the arsenic case. Okay, the next one is the phosphorus profile, and then we are going to spend a little bit more time on the phosphorus, because the phosphorus case, it shows a little bit complicated than the arsenic case. Any questions? All right, and then I'll see you on next Monday. Okay?